Hello everyone and welcome back. Well, in the previous lecture we have elaborately discussed about the bipartite graph and a very particular type of bipartite graph, that is the complete bipartite graph. We have learnt the representation of a complete bipartite graph as KMN, where M and N in the subscript indicate the order of the partite sets in the complete bipartite graph. Well, towards the end of the previous lesson, I have posted one numerical problem based on complete bipartite graphs for your practice, which I am supposed to solve in the very beginning of this lecture. So let's first go through the solution of that particular problem. Before that, let's have a look at the numerical problem once again. The question was that there is a complete bipartite graph KM12 having size 72. We have to determine the value of the variable m as well as the order of the complete bipartite graph. So let's see the solution to this problem. First, we will list down the given conditions. So we are given a complete bipartite graph KM12 such that its size is given as 72. Our job is to find the value of the variable m and the order of the complete bipartite graph. So in the given problem, we have been provided with a complete bipartite graph. The representation itself indicates it is a complete bipartite graph with m vertices in one partite set. I don't know the value of m. I have some m vertices in one partite set, and in the other partite set I have exactly 12 vertices. That quantity I know. So these are the two partite sets with names, suppose U and W, U containing these m vertices in one partite set and W is a set containing these 12 vertices of the other partite set. Now since it is KM12, that is a complete bipartite graph, so every vertex of the set U is adjacent to all the 12 vertices of the set W. There are 12 vertices below, okay. In this way, every vertex of U is adjacent to all the vertices of the other partite set, that is W. Now that will help us to determine the degree of every vertex in this graph. So if we look at the vertices of the partite set U, we know every vertex being adjacent to all the 12 vertices below, the degree of the vertex is 12. Like this, the degree of every vertex in this partite set U will be 12, because that is how we construct our complete bipartite graph, by making every vertex of one partite set adjacent to all the vertices of the other partite set. So since we know that there are 12 vertices in the other partite set, so we know that every vertex of U is going to have the degree 12 each. And we have discussed in the previous lecture that we can find out the size of any bipartite graph, be it complete or not. We can find out the size of any bipartite graph by summing up the degrees of the vertices of any partite set. So here, for example, if we see the vertices of the partite set U, and if we sum up the degrees of all these vertices of the partite set U, we will get the size of this bipartite graph. So summing up all the degrees of all the vertices in the partite set U, I am getting 12 plus 12 plus 12. How many times? Since there are m vertices, so this sum goes for m times. So I am getting 12 plus 12 plus 12 up to m times. That is what will determine the size of this complete bipartite graph. Now by the given problem, the size is provided to me as 72. So this is nothing but equal to 72. This is what I have determined the size of the complete bipartite graph. For any bipartite graph, the size can be determined by summing up the degrees of all the vertices in any one of the two partite sets. The same thing we could have done with respect to W also. In W, every vertex is having degree equal to m, because every vertex of W is adjacent to all the m vertices in the other partite set U. So every vertex in W is having the degree m. If we take the sum of the degrees of all these 12 vertices, we are having m plus m plus m up to 12 times. That is the sum of degrees of all the vertices in the partite set W, and that will also give us the same size of the graph. So this summation is nothing but 12 times m is equal to 72. If we solve this problem, we get the value of m as 72 by 12, that is 6. So the value of m is obtained as 6. So that is the solution of one part of the problem. Now the second part of the problem is to determine the order of this graph. Now the moment we know the value of m, we know the complete bipartite graph is K612. We know that the order of any complete bipartite graph Kmn is m plus n, because there are m vertices in one partite set and n vertices in the other partite set. So the total order is the total number of vertices, that is m plus n. So for K612, the order of K612 will be 6 plus 12, that is equal to 18. So the complete solution of the problem would be m is equal to 6 and the order of the complete bipartite graph K612 is 18. So this is the solution to the problem that has been presented in this slide as well. Now let's continue with today's lecture, and the topics of discussion today include the very first lemma of graph theory, that is the degree sum formula, and very popularly known as the handshaking lemma. Along with the degree sum formula, we will also be discussing several other lemmas and corollaries as an application of the handshaking lemma. So without any further delay, let's start today's lecture, and the very first topic of discussion today is the handshaking lemma, also known as the degree sum formula. So let's see what the degree sum formula is all about. Let me first draw a graph and explain it to you. You can draw any graph you want, be it simple, multi, pseudo, complete, bipartite, any type of graph. Suppose this is my graph G. The vertices are named as A, B, C, D, E and F. Let us now find out the degrees of all the vertices in this graph. Let me write the degrees within brackets. So the vertex A has degree 3, B has degree 2, C has degree 4, D is a pendant vertex of degree 1, E has degree 2 and F is also a vertex of degree 2. Now let us find out the sum of all the degrees of the vertices. So we sum up all the degrees, that would be equal to 3 plus 2 plus 4 plus 1 plus 2 plus 2, that is equal to 14. So the sum of all the degrees of the vertices is 14. Now let us count the size of this graph. So we have 1, 2, 3, 4, 5, 6, 7 edges in the graph. So we have 7 edges in this graph, and this 14, that is sum of the degrees of all the vertices, is nothing but equal to 2 times 7. That is 2 times the number of edges present in the graph. And this is what happens for any graph, that is sum of the degrees of all the vertices is equal to twice the number of edges in the graph. And you can check this out for any graph, be it simple graph, be it multi, pseudo, edgeless, complete, bipartite, any type of graph you can take and you can check this particular formula. You will find that for any graph, the sum of the degrees of all the vertices is equal to twice the number of edges in the graph. That is, if we add the degrees of all the vertices in the graph together, what we get is nothing but 2 times the number of edges in the graph. This is what is called the handshaking lemma or the degree sum formula. Let us now see the mathematical expression, how we express this degree sum formula mathematically. So what we are doing is we are adding up the degrees of all the vertices. So how do we represent degree of a vertex? D of V. This is how we represent the degree of any vertex. Now if we are to take the sum of all the degrees, we have to put a summation on this degree, and this summation will run for all the vertices of the graph. So if you are dealing with a graph G, then for every vertex belonging to the vertex set of G, if we take the summation over all the degrees, that we are adding up all the degrees of the vertices, it will be equal to twice the number of edges, that is the size of the graph denoted by EG. This is what is the degree sum formula or the handshaking lemma. So let's see the statement. If G is a graph, then the sum of the degrees of all the vertices in G equals twice the number of edges. This is the mathematical expression where V denotes any vertex in the graph, capital VG indicates the vertex set of the graph, and EG indicates the size of the graph. Now this is the handshaking lemma, and we need to know the proof for this lemma. So let us see how we can prove this. So basically, when we have dealt with the degree of a vertex, we have discussed that every edge contributes 1 degree to each of its end vertices. That is, in totality, an edge contributes a total of degree 2 to both the end vertices. That is why when we take the sum total of the degrees of all the vertices in the graph, since every edge has its contribution of degree 2 in it, so its sum total of degrees becomes twice the number of edges. As many edges are there, twice that number will be the sum total of all the degrees, because every edge is contributing a total degree of 2 in the sum of the degrees. So that is what is written in this slide only as the proof to the handshaking lemma. that every edge contributes 1 to the degrees of each of its endpoints, that is, overall every edge contributes 2 to the sum of the degrees of all the vertices, and hence we get this result that is presented in the degree sum formula. Now let us see some corollaries as an application of the degree sum formula. The first corollary, and a very important one, is that every graph has an even number of odd vertices. Meaning, take any graph, you will find the number of odd vertices in the graph is always even. Now what do we mean by odd vertices? An odd vertex means a vertex having odd degree. So in a graph, if you count the number of odd vertices, that is, count how many vertices are having odd degrees, that count will always be even. Let us see one graph. Let me draw a pseudo graph now. Suppose this is my graph G with vertices A, B, C, D. Here I can see the degree of the vertex A is 4, degree of B is 3, degree of C is 4 and degree of D is 1. It is a leaf. So here we can see there are two even vertices A and C who are having even degrees, and there are two odd vertices B and D who are having odd degrees. So these are the odd vertices. B and D are the odd vertices. So how many odd vertices do we have? 2. This count is 2 and this count is even. So that is what the corollary is. In any graph, the number of odd vertices that you have is always even. So here we have 2 odd vertices. You can take any graph you want. Suppose this is my graph G where the vertices are x, y, z, w, u. So the degrees of the vertices are x has degree 1, y has degree 3, z has degree 1, w has degree 3 and u has degree 2. See, in this graph there are 5 vertices in total, out of which u is the even vertex and each of x, y, z, w is an odd vertex. So how many odd vertices do we have? 4. This count is always even. The number of odd vertices in a graph is always even. So this is what we need to prove, and we will prove this applying the degree sum formula. So let us prove this corollary. Now remember one thing, whenever you are asked to prove something, give a generalized proof, give the generalized logic. Do not pick up any particular graph and show that for this particular graph this holds true, hence it is proved. No, this is not how you prove something. When a statement is true, it is universally true. That is supposed to hold for every graph. So we cannot pick any particular graph and show that for this it is true. We have to give a generalized logic that it will hold for any graph G. So to prove this corollary, take any graph G. Suppose G is a graph with vertex set Vg. Now what we will do is, we will divide this vertex set Vg into two subsets. So Vg is divided into V1 union V2, where V1 and V2 are two subsets that I have formed from Vg. Now what is this V1? V1 I have taken as the set of all the odd vertices. So V1 contains of those vertices of Vg which have odd degrees, and V2 is the set of all the even vertices. So it contains all those vertices of Vg which have even degrees. Now just it follows from the degree sum formula or the handshaking lemma that sum of the degrees of all the vertices is equal to twice the number of edges in the graph. V belongs to the vertex set Vg. So this is my mathematical expression for the handshaking lemma. What I will do, I will break this summation on dv over the entire vertex set Vg into two different summations separately. First summation will take the sum of the degrees of all the odd vertices. So for all the vertices V belonging to V1, it takes the summation. And the second part, it is taking the summation of the degrees of all the vertices which belong to V2. So basically sum of the degrees of all the vertices in the graph have been taken separately as sum of all the degrees of the odd vertices and sum of the degrees of all the even vertices. That is equal to twice the number of edges again. Now what? Separate out this quantity dv summation V belongs to V1. This is equal to twice of Eg. Take this quantity this side. So we have minus summation of dv V belongs to V2. Now observe this equation carefully. So let me write it again. Summation of dv V belongs to V1 is equal to twice the number of edges in the graph minus summation of dv V belongs to V2. So if we observe the right hand side of this equation carefully, we will see there are two terms, out of which the first term is twice Eg. Eg is the size of the graph, that is the number of edges present in the graph, which is a non-negative quantity, it is a count. 2 times of any non-negative quantity is going to provide us an even quantity. So, this is an even integer, no doubt. What about the second term? Here we are having a summation of all the degrees of those vertices which are belonging to V2. Now, V2 is the set of all even vertices. So, V2 contains only those vertices which have even degrees, and those even degrees are being added here. So, this is basically sum of all the even degrees of the graph, that is, it is the sum of all even quantities. Now, when even integers are being added, the resultant is also an even integer. So, this is also even. So, in totality, the entire right hand side of this equation is even. Now, since this right hand side is equal to the left hand side, so no doubt this quantity is also going to be an even integer. Now, visualize what this quantity is actually all about. This is the summation of the degrees of all the odd vertices in the graph. Capital V1 is the set of all odd vertices. Now, those odd vertices are all having odd degrees, and those degrees are being added here. So, this is basically taking the sum of some odd integers, but the resultant sum is coming out as even. Now, when is it possible that you are adding odd integers one by one and the resultant is even? That is possible only when you are adding an even number of odd integers. That means this summation contains an even number of terms. Every term is odd, but since there are even number of terms, that is the reason the total quantity as a whole is coming out as even. So, if you are having even number of terms in this summation, that means the number of vertices small v in the set capital V1 is even. So, capital V1 has even number of vertices. Now, capital V1 is the set of all the odd vertices. That means the number of odd vertices in the graph is even. That is the proof of this corollary, that in any graph, the number of odd vertices that we have, that is always an even count. So, this is how the proof goes. We divide the entire vertex set Vg into V1 and V2, where V1 is a set of all odd vertices and V2 is a set of all even vertices. Then by the degree sum formula, we have sum of all the degrees is twice the number of edges. Now, we divide this summation into two parts, one summation comprising of all the degrees of odd vertices and another summation which is taking the sum of all the degrees of the even vertices, that is twice the number of edges. Now, keep this part on one side and take this on the other side, so we get this equation. While observing it carefully, we found this quantity is even, this quantity is also even, which makes the total difference of two even quantities even, and hence this left hand side is also an even integer. So, here we are actually adding a certain number of odd integers, but the resultant is even, means the number of odd integers that we are adding, that is even. And here we are adding the degrees of the odd vertices. So, there are basically an even number of odd vertices in the graph. That is why the resultant is an even quantity. So, we can check this out in an example. Suppose we have any graph G, vertices are A, B, C, D and E. Here the vertex A has degree 1, B has degree 2, C has degree 2, E has degree 1 and D has degree 2. So, there are 3 even vertices and the number of odd vertices are 2. There are 2 odd vertices in the graph. So, this count of odd vertices in the graph is always even. And at the same time, we can check our degree sum formula also. So, here sum of all the degrees in the graph is equal to 1 plus 2 plus 2 plus 1 plus 2, that is 8, and we have the size of the graph as 1, 2, 3, 4 edges are there, and this 8 is nothing but twice of 4, that is twice the number of edges in the graph. So, this is the degree sum formula that also we have verified in the same graph. Now, let us move to another corollary, that is a k regular graph with n vertices has n k by 2 edges. So, basically we have a k regular graph. What does it mean? A graph in which every vertex has the same degree and that degree value is k, and it has n vertices. So, the order of the graph is given as n. We have to prove that the size of the graph is nk by 2. Let us see how we can prove it. So, let us list down what is given to us. We have been provided with a graph G whose order is n. G is k regular, that means every vertex is having degree k. So, let us write it. So, the degree of every vertex in the graph is k. This is true for all vertex V belonging to the vertex set Vg. Now, what is to be proved? So, we write it under required to prove. In short, we term RTP. So we need to prove that the size of the graph is nk by 2. Now we start our proof. So this is how we can have a format of proving something. First, in the given part, you list down whatever information has been provided to you. Then in the RTP portion, you write whatever you need to find out or whatever you need to prove. Then you come to the proof part where we will give our logic and prove something. So the proof goes like this. See, the graph is k regular, so every vertex is having degree k. So if we use the degree sum formula, we have sum of the degrees of all the vertices in the graph is twice the number of edges in the graph, right? Now here we know that the degree of every vertex is k, dv is k. So this summation runs over k. And how long does it run? It runs for all the vertices in the vertex set, and we know there are n vertices in the vertex set, because the order of the graph is n. So this summation goes n times. That means we have k plus k plus k n times. The degree of every vertex is k and there are n vertices in total. So the sum of the degrees of all vertices is k plus k plus k up to n times. That is twice the number of edges. So this is nothing but n times k, that is twice the number of edges. So from here only we get the size of the graph, that is number of edges is nk by 2. Proved. So let's see the proof in this slide. See, the degree of every vertex is k here. So by the degree sum formula, it's just the application of degree sum formula. You apply it. You use the idea that the graph is k regular, so every vertex has degree k and there are n vertices in the graph, it's given. So the summation goes as nk. That is equal to twice the size, so size comes as nk by 2. Now let's check the result of this corollary with an example. So we need a k regular graph, so let us take a 3 regular graph. So every vertex should have degree 3. So I can make a k4. I know k4 has every vertex of degree 3. So this is A, B, C, D, every vertex is having degree 3. So here my k is 3 and the number of vertices, that is n, is 4. And what is nk by 2? Nk by 2 is 4 into 3 by 2, that is 6. Okay. So now check how many edges you have in the graph. 1, 2, 3, 4, 5, 6. You have 6 edges. So size of the graph is nk by 2. In any k regular graph with n vertices, the size is nk by 2. Now the next lemma, that is, if k is greater than 0, then a k regular bipartite graph has the same number of vertices in each partite set. What does it mean? So we are given a k regular bipartite graph. So k is a positive integer given and we are dealing with a bipartite graph here in which every vertex is having degree k. We have to prove that in this bipartite graph, the two partite sets have the same cardinality. That is, there are same number of vertices in both the partite sets. So let's see the proof to this lemma. So again we list down the given conditions. Let G be our k regular bipartite graph. So G is a bipartite graph in which every vertex has degree k and it's given that k is greater than 0. So required to prove the RTP is that G has same number of vertices in the two partite sets. So how do we prove it? So let us take the two partite sets of G. U is one partite set and W is the other partite set. So these are the two partite sets. So what we need to prove is that cardinality of U and cardinality of W is same. That is, they are containing the same number of vertices. Okay. So G is a bipartite graph in which we have two partite sets, U and W. We don't know how many vertices are there in each partite set. We have to show that the number of vertices is same. Now G is bipartite with two partite sets and it is a k regular graph. So every vertex, be it in the partite set U or be it in the partite set W, every vertex is having the degree k because the graph is k regular. Now we know in any bipartite graph, we can count the number of edges in the graph, in the bipartite graph, by summing up the degrees of all the vertices in one partite set. So we have two partite sets U and W. So we can sum up the degrees of all the vertices present in U, that will give us the size of the bipartite graph, or we can sum up the degrees of all the vertices in the other partite set W, that will also give us the size of the bipartite graph. So we will compute the size of the bipartite graph in either ways. So let us first compute it with respect to the partite set U. In the partite set U, how many vertices are there? I don't know the count. So, let us indicate it by the cardinality of the set itself. U is the set of the vertices in the partite set. So, the cardinality of U indicates the number of vertices present in that set. So, these are the number of vertices present in the partite set U. Every vertex is having degree k. So, the sum of the degrees of all these vertices in the partite set U would be ku. Every vertex is having degree k. So, sum of degrees would be k plus k plus k. How many times? As many vertices are there. There are cardinality of U number of vertices. So, k multiplied by cardinality of U, that will give us the size of the graph. Now, if we compute the same size of the graph with respect to the other partite set W, then in W there are cardinality of W, these many vertices, and every vertex is having degree k because graph is k regular. So, if we sum up the degrees of all the vertices of this partite set W, we get k plus k plus k. How many times? As many vertices are there in W, and there are cardinality of W number of vertices. So, we have the sum of degrees as k multiplied by cardinality of W. Now, this will also give us the same size of the graph G. Now, from these two equations, we can write k cardinality of U is equal to k cardinality of W, because the right hand side is same in both the equations. Now, since it is given that k is greater than 0, so we can cancel out k from both sides, and we are left with cardinality of U is equal to cardinality of W. That is, the two partite sets have the same number of vertices, and we are done with the proof. So, let us go through the proof once again. G is a k regular bipartite graph, partite sets are U and W. So, we count the number of edges according to their endpoints in the partite set U first. So, in the partite set U, these are the number of vertices present. Each vertex is having degree k. So, sum of all the degrees is k times the number of vertices, that is k times cardinality of U. That will give us the size of the bipartite graph, because this is how we calculate the size of any bipartite graph, by finding out the sum of degrees of all the vertices in one partite set. The same thing if we do with respect to the other partite set W, then we get the size of the graph in terms of the cardinality of W. Now, with the help of these two equations 1 and 2, we arrive at this, and since our k is greater than 0, so we can cancel out k and we get that the number of vertices in the two partite sets are same. Let us see this with an example. So, let me draw a k regular bipartite graph. Let us draw one regular bipartite graph. So, we have, see, we can have a one regular bipartite graph. Graph is bipartite, no doubt, and every vertex is having degree 1. See, we have the same number of vertices in both the partite sets. Here also we have two vertices, here also we have two vertices. We can count the number of edges in the bipartite graph by summing up the degrees of the vertices in one partite set. So, degree of A is 1, B is 1. See, sum of degrees 1 plus 1, 2. You have two edges. Same thing you can do with respect to the other partite set. Degree of C is 1, degree of D is 1. Sum of the degrees is 2. That is the number of edges in the graph. So, this property holds for any bipartite graph. If we sum up the degrees of the vertices in any partite set, it will give us the size of that bipartite graph. So, that is what we have taken the help of to prove the lemma. So, there are a few points to remember here. First of all, in any graph G, as we have seen the degree sum formula, that is the sum of the degrees of all the vertices is twice the number of edges. Now, twice a count means it is even. That is, the sum of the degrees of all vertices is always even. In any graph, if you sum up the degrees of all the vertices, it is always even because it is twice the number of edges. Next point is, no graph of odd order can be regular with odd degree. Why? Because in a graph, in any graph, the number of odd vertices is always even. So, you cannot have an odd number of odd vertices in a graph. So, a graph of odd order, that is where you have odd number of vertices in the graph, it can never be regular with odd degree. That is, if you are dealing with a graph having odd number of vertices, it can never be a regular graph with an odd degree. That is, it can never be k regular where k is odd, because in that case, every vertex will have that odd degree k and there are odd number of vertices. So, the sum of the degrees of all the vertices would be odd, because you will be adding odd integers odd number of times. That cannot happen because sum of degrees of all the vertices should be even. Now, let us look into some solved problems, basically numerical problems based on the degree sum formula. and all the lemmas and corollaries that we have discussed today. So the first problem is, there is a 3 regular graph G having order 8. We have to find out the size of the graph. So let's list down what is given to us or provided to us as an information. We have been given that G is a 3 regular graph. Immediately write what you understand. 3 regular graph means degree of every vertex is 3 for all vertex in the vertex set. And we are given the order of the graph as 8. We need to find the size of the graph, e.g. So how do we solve it? It is just application of degree sum formula. So we know sum of the degrees of all the vertices in the graph is equal to twice the size of the graph. This is the degree sum formula or the handshaking lemma. Now the degree of every vertex is known to us as 3 because it is a 3 regular graph. So we take the summation over 3 for all the vertices in the graph, that is twice the number of edges. Now how many vertices are there? Order is 8, so there are 8 vertices. So this summation goes 8 times. So we are adding 3 plus 3 plus 3 8 times. So that is 3 multiplied by 8 is twice the number of edges. It gives us the size of the graph as 24 by 2, that is 12. So this is the answer to the problem, that the size of the graph is 12. Let's see the solution. Here we have applied the degree sum formula. Degree of every vertex is 3. Summation runs for 8 times because there are 8 vertices in the graph. So we get 24 as twice the number of edges. So number of edges is 12. Now we can alternatively solve the same problem with the help of a corollary that we have studied today. We have studied today that a k regular graph with n vertices has nk by 2 edges. So we could have used that corollary, that result, directly to obtain the solution. We know a k regular graph of order n has nk by 2 edges. So in this case we have been given a 3 regular graph, so k is 3, order of the graph is given as 8, so n is 8. So the size of the graph will be nk by 2. Directly you can put the result of the corollary. So we have n is 8 multiplied by 3 by 2, that is 12. So we can directly get our answer with the application of the corollary also, which again follows from the degree sum formula only. So this is the alternative solution that we have shown here using the statement of the corollary. In the next problem we have been given a graph G having order 14, size 27. Degree of every vertex is either 3, 4 or 5. So all the vertices that are present in the graph, they have either degree 3 or degree 4 or a degree 5. There are 6 vertices of degree 4 and we have been asked to find out how many vertices are there of degree 3 and how many are there of degree 5. So let us list down what has been provided to us. The order of the graph is given as 14 and the size of the graph is 27. The degree of any vertex is either 3 or 4 or 5. No other degree is present for any vertex in the graph. And what else? We know there are 6 vertices of degree 4 each. Now we need to find how many vertices are there of degree 3 and how many are there of degree 5. So let us assume that there are x vertices of degree 3 each and there are y vertices of degree 5 each. So we need to find the values of x and y. Okay. So how do we solve this? See, we are having 14 vertices in total, that is the order of the graph. There are 6 vertices which are of degree 4. I have assumed there are x vertices of degree 3 and there are y vertices of degree 5. And these are the only degrees possible. So 6 plus x plus y, that is the number of vertices of degree 4 plus the number of vertices of degree 3 plus the number of vertices of degree 5. These are all the vertices in the graph. So that is equal to the order of the graph, that is 14. So from here I get an equation that x plus y is equal to 8. Let's keep this. What else? Now we can apply the degree sum formula. So here we have 6 vertices of degree 4 each, x vertices of degree 3 each and y vertices of degree 5 each. So if we take the sum of all the degrees of the vertices, we get 6 vertices of degree 4 each. So that is the sum of the degrees of all those 6 vertices. Plus there are x vertices of degree 3 each. This is the sum of the degrees of all those x vertices. And there are y vertices of degree 5 each. So this is the sum of the degrees of all those y vertices, and there are no more vertices in this graph, and their degree sum is nothing but twice the number of edges in the graph, and size, that is number of edges, is 27. So from here we get 24 plus 3x plus 5y is equal to 54, which can be simplified as 3x plus 5y is equal to 30. So this is another equation in xy that we have obtained. So we get two equations in two variables. One is x plus y equal to 8 and other is 3x plus 5y is equal to 30. So we can solve this system of equations, two equations in two variables easily. Here we have y is equal to 8 minus x. So here we put, in place of y, we put 8 minus x. And if we solve it, we get 3x plus 40 minus 5x equal to 30, which gives us 2x is equal to 10, that means x is equal to 5. As soon as x is equal to 5, y is 8 minus x, so 8 minus 5, that is 3. So there are 5 vertices of degree 3 each and there are 3 vertices of degree 5 each. That is the solution to our problem. Go through the solution. Order is given, size is given, there are 6 vertices of degree 4 each. We assume there are x vertices of degree 3 and y vertices of degree 5. So there are 6 plus x plus y vertices in the graph, that is the order of the graph 14. From here we obtain one equation and we use the degree sum formula. So if we find out the sum of degrees of all the vertices, we have the categories of degree 3, degree 4 and degree 5. So we sum them up separately. So we have 6 vertices of degree 4 each, x vertices of degree 3 each and y vertices of degree 5 each. That sum gives us the twice the number of edges by degree sum formula. If we simplify this and use the previous equation of x and y, we can solve for x as 5 and we will obtain y as 3. So x, that is the number of vertices having degree 3, the count is 5 and there are 3 vertices having degree 5. Now we have arrived at the problem for practice session. So again I will be posting one problem, one numerical problem based on the degree sum formula that we have studied today. So let's see the problem. We have been given a graph G whose order is 5 and size is n. So number of vertices is 5 in the graph and number of edges is 9. There is one vertex of degree 5, one vertex of degree 1 and the remaining vertices in the graph have the same degree x. You have to find out the value of x. Go through this question once or twice and then list down all the given information, list down what you need to find out and then go to the solution to this problem. So you can solve this numerical problem and post the answer in the comment section below. Definitely I am going to solve this and explain to you the entire solution in the very beginning of the next lecture. So that's all for today. I am going to meet you again in the next lecture. I really hope that you are enjoying these lecture series on graph theory. Still, if you have any queries and suggestions, then you can write in the comment section below and let us know. In the meantime, if you love learning with me, then please do like, share and subscribe to our channel. Till then, thanks for watching. Take care and bye-bye.